All right, let us look at this problem called lexicographically smallest equivalent string. So what's given in this problem is that we are given two strings and we are told that these two strings are equivalent. And based on that, you build the mapping. So for example, in this case, we're giving this S1 ABC and S2 equals to CDE are equivalent. That means character A and C are equivalent, character B and D are equivalent, character C and E are equivalent. And for equivalence, there are these properties that we'll follow. That means if it's a character is equivalent to itself, if A is equals to B, then B is equivalent to A. And then transitivity, if A is equivalent to B and B is equivalent to C, then A is equivalent to C. So based on this, we have to create the equivalence relations, and then it gives us a third string, this base string, and it asks us to find the smallest equivalent string for that string. So let me give an example to clarify, or use the same example from the problem to clarify. So for example, it says that hey, ABC and CDE are equivalent. So based on that, build your relationships, and finally give me the smallest equivalent string for EED, right? So to give the smallest equivalent string, basically I want to check if E can be replaced by something smaller, right? Similarly, basically we want to find out if all these characters can be replaced by something smaller, right? And let's see this what relationships we get from here. So we get that A and C are equivalent. We get that B and D are equivalent. We get that C and E are equivalent, but C is also equivalent to A. So we could also do something like A, C, and E. All three are equivalent, right? So we get these two relationships. Now look at E. Is there E can be replaced by something smaller? Yeah, the E can be replaced by something smaller, which is A, right? So A. And what about this D? Well, this D can be replaced by B. So this will be the smallest equivalent string for EED. Let's look at another example. So we're given this two strings. One is Parker and other is Morris. We are told that they are equivalent, and we have to finally find the smallest equivalent string for this guy, parser. Okay, so let's first build the equivalent relationships. So from here we get hey, M and P are same, A and O are same, R and R are anyway same, we can ignore that. Then it says R and K are same, so I'll keep the smaller one to the left. And E and I are same, okay. And R and S, I is already there, so K, R and S are all same. So these are the mappings now we have. Based on these mappings, let's find the smallest equivalent string for this. So P, well, P can be replaced by M. A is anyways the smallest. R can be replaced by K. S can also be replaced by K. E, there is no E, there is E, but there is no smaller, so E remains E. R can be changed to K, which is a smaller one. So this is the smallest equivalent string for parser. So that's the logic, right? Oh, that's the problem. Now, how can we do that? We'll discuss two approaches to it. Essentially, we have to build these mappings somehow, right? And once you build these mappings, then we just have to use those mappings to replace the string. So how do we build these mappings? We can just build a graph out of it, right? Based on all of these, we can just build an edge between all of these nodes, right? So in this case, which is exactly what. So this is our graph. This is how our graph will look like, right? And then what do we do? Well, for each and every for the graph, we'll have different connected components, right? We'll find out each and every connected component, and for every connected component, we'll assign the connected component ID as the smallest one within them. So this representative is A, its representative is O, sorry A, its representative is K, its representative is I, right? And now so we will maintain this. I don't know what to call it. Let's say the we can call it root, right? For every character, we'll maintain this root for every character, and it will point to initially to itself, and then based on these connected component mappings, we'll change them, right? So that's the general idea. So we'll do how to build the connected component. We'll do a DFS starting from A to Z, and uh, whatever A can whatever A can reach. So in this case, A can reach itself and O. So for both A and O, the connected component ID will become A. And then we'll go to B. B does not match to anything, so B's connected component ID will remain B. And then similarly, when we come to let's say M, so M can also reach P. So for both M and P, we'll set the connected component ID as M, and so on and so forth. And then later on, when we're changing the string, we'll just find for each and every character what is its connected component ID. And whichever the connected component ID is, that will be the smallest, and we build the logic based on that, right? So let's use this approach and solve the problem. So the first we have to build the graph. Now to build the graph, we can use adjacency matrix or adjacency list based representation. Because the number of nodes are just 26, we can just simply use the adjacency matrix based representation here. So let's do that. So let's say we do Boolean connected, I'll say, or has edge, right? Just call it edge. So if there is an edge between two nodes, then it will be true, otherwise it will be false. So we go Boolean the number of characters 26, 26. Now let's go through each and every string. So for int I equals to 0, each and every character rather, s1 dot length I plus plus. What we want to do is we're going to say, so we get the character, so c1 equals to s1 dot caret I, and c2 equals to s2 dot caret I. Now we'll just link both of them. So we'll say edge of c1, c2 equals to true. Obviously, we want to convert them to index, zero-based index. So we'll do like this. All right. And we want to make it undirected. So we'll also do so we build this adjacency matrix-based representation. Now we want to give like a connected component ID, right? Let's call it. So we want to give a specify a character. We'll call it root char, right? Let's call it root. So my root is equals to um, let's call it connected component, right? So connected component equals to new char of size 26. How do we initialize it? We don't need to. We'll do the while doing the DFS we can initialize. Okay, that's fair. And then we want to also maintain maybe a visited array. So boolean visited equals to new boolean of size 26. Now let's go through each and every character. So I equals to 0, I is less than 26, I plus plus. Now what do we want to do here? So we want to go if not already visited, then we're gonna do DFS. In the DFS we can pass in this I. We can pass in the edge array, the connected component, the visited array, and we'll pass this character itself, which will be what? Which will be char of I plus. Why do we pass this character? Because this is the smallest one, right? We are going from 0 to 26. So this is the smallest unvisited one. So everybody that I can visit from this will assign their connected component as this guy, as the smallest guy, right? That's the general idea. So we put this now. Okay, let's say we do that. After that, what will we do? So we'll update the new string that is given to us. So we'll go through each and every character of the new string. So for each character of this base string, we're gonna find its smallest equivalent character, right? The smallest equivalent character is represented by this CC guy. So CC of this, we get the smallest equivalent character of that, and that's it, right? So we return speed or to string. Okay, now let's do the DFS as well. So we will void DFS. So what else is passing is, so index, we have a Boolean array representing whether there is an edge or not, and what else? The connected component array, a visited array and the min char, right? That we want to assign to min equivalent char, right? Okay, so if it's already visited, then we don't care, right? So if visited, then we should just ignore. It's already marked, all is good. Do we need a visited array? Because yeah, okay. I mean, we don't really need it. We could use based on the CC array itself. Um, but yeah, okay, we'll have to initialize a CC array to something other than between 8 to 26. Yeah, okay, I'll ignore that space bit. Okay, so visited, if it's already visited, then we ignore. If it's not already visited, then then we mark it visited. We mark the connected component as this min char, which belongs to the connected component represented by the smallest character. And now we want to go through all its children, right? So or all its neighbors. So let's do a loop from to all characters, and you don't want to do for itself. So if I is equals to index, well, ignore that bit. And other than that, you want to go to all the letters which are connected to you. So if there is an edge, well, then also shouldn't be visited. Well, visited is taken care of here, so that's fine. You just want to check if there is an edge. So if there is an edge between I and j, then you want to try not I and j, I and index. Then you want to try out this DFS from I. Okay, pass on everything else. Fair enough. So we do the DFS like that, and I think that's it, right? So let's run. Fix few errors. Line number 3, spelling mistake. And line number 25. Okay, there is some issue in the line numbers. Let's run again and get to the line numbers. Okay, here for character C in base string, some minor syntactical thing. Let's run again. Okay, the 3 test cases passed. Let's submit. And it works. So that's one way of doing it, through just making connected component via DFS. There is another way that I want to talk about, and let's talk about that as well, which is the concept of union find. So union find, or it's also called disjointed set union. So what's really given to us initially, if you think about it, we have a set of 26 different characters, right? Each individual character, A, B, C till Z. And then we are given, hey, there is some linking. So you join or you unite certain sets, right? So for example, we are given this Parker and Morris, right? And we have to unite those sets. So now we have to unite P and M. Then we have to unite A and O. So essentially, we could use the union find sort of data structure to essentially run these different union operations, right? So we have to do union P comma M, then we have to do union A comma O, then we have to do union R comma R, and then union K comma R, and so on and so forth, right? Now let's talk about how union find data structure looks like. So the way that union find works is initially, so there is a parent child relationship. So for every node has a parent. So there is a parent array, and every node has a parent. So for any, to begin with, A's parent is itself, B's parent is itself. Initially, parent of I equals to I, right? And then when you are joining something, uh, so when you do union, what you do is you find the root of A, you find the root of B. So this is R1, this is R2. What is the root? Let's say A's parent is B and B's parent is C. and let's say there is a D's parent is E, E's parent is F. Let's say that's the relationship that we have built so far. And now if I have to, let's say, do this operation called union A comma D, well, I won't link A and D because A already has a parent, B already has a D already has a parent. So we'll go to the root of those trees. So for root of A would be C, root of D would be F. So now we link C and F. Initially currently both C and F parent are itself. Now one of them will link to another. Typically, who will be the made the child and who will make the parent? Usually, in union find, we want to keep smaller uh, the smaller tree as the child, right? So that our tree's size do not grow. For example, let's say there is a this big tree and there is another this big tree. Now, uh, which would be better, adding this tree to itself as a child, or adding the smaller tree as a child? So always adding a smaller child is the better. But in this case, the number of nodes are just 26, and what you want to do is you want to find out for every node which is a minimum equivalent character, right? So to get to the minimum equivalent character, what we'll do is we'll keep the smaller one. So between C and F, whichever is the smaller one, we'll keep that as the parent. So in this case, C is a smaller one, so we'll keep C as the parent, and we will change this to, we had, so now C, another child of C would become this F, right? And we have this E, D, and we have this B, A, right? So that's now if somebody says, hey, what is the minimum equivalent character for E? Well, I go to the root of it. So to find the minimum equivalent character is finding the root, and joining is essentially joining the roots, right? And the union operation is connect the roots. So let's use this disjointed set union using this concept of having parent and union by joining the roots, that approach, and solve the problem using that as well. So if we go back to code, clean the only original DFS related code that we wrote. So what we're saying is we'll for the union find operation, we maintain like a parent array, right? So let's maintain a character array parent. Uh, And let's say just initialize it within the function so that we don't have to pass the parent. That's why I kept it outside. So I have a new char of size 26. And initially we set each node as its own parent, right? So we go for each, for int I equals to 0, I less than 26, I plus plus. My parent is myself. That means parent of I. This I represents the index 0 represents character A, right? So its parent of I, parent of I would be what? Would be so type equals to char. You can do like this A plus I, right? So each guy is parented itself to begin with, and now we wanna, what do we wanna do now? So now we wanna do for each. Um, let's go through each and every string, right? So I equals to 0, I less than s1 dot length, I plus plus. And what we really want to do is we want to join the two. So we want to union s1 dot char at I and s2 dot char at I, right? Somehow we want to join the two, and now we all of them we have joined. And then what we want to do is we want to use the relationship. So string builder sp equals to new. Now we go through each character of this base string. So for each char C in the base string, what do we want to do? Well, we'll append the minimum equivalent character, right? So how do we get the minimum equivalent character? Well, it will be the root of this node C, right? So there are a few things that we have to implement here. We have to implement this union and we have to implement this root. So let's implement those. But before that, okay, here we do this and we just do, okay, return this string build that we built. It's that easy, right? So looking at it looks much easy to implement. Now let's see how do we implement the root function. So root is quite easy. So we have to return the root character. for a given character. So we'll just keep going to its parent, to its parent, to its parent, right? So we do, okay, while your parent, while parent of C is not equal to C, and obviously we're going to convert this into, so that really means I have a parent, so I go to that parent. So then C equals to parent of C, right? And eventually we'll get to the root which whose parent it itself, and that is what we will return. And similarly, now we want to do union. So we have a union operator. So we have two characters, A and character B. And the way to do the union is, well, you first find their roots. So R1 is root of A and R2 is root of B. And now what do we do? Whichever is the smaller. So if R1 is less than R2, we want to keep the smaller guy as a parent. So that means then parent of R2 equals to R1. And obviously we have to take care of the indexing bit, right? Else, okay, else you want to do parent of R1 as R2. And I think that's the entire code, right? So let's run and fix any issues. Okay, the three test cases pass. Let's submit. And this works as well. Now, I wonder if there is some small optimization called this path compression that we typically do in the union find, which is where if you are trying to find the root of a parent, like, okay, let me quickly go back to the whiteboard. There is a small minor trick that we typically do in union find, which is called path compression. And we do two things usually. One is we do weighted union find, which we are not doing here. And the weighted union find is essentially, the idea basically here is always add the smaller tree to larger tree. And the way to do that would be, for every root, we have to also maintain the length of the tree, right? The number of nodes in the tree. But anyways, we are not doing this here because in our case, we want to keep the root as a smaller character just for the simplicity. What is path compression? Path compression is essentially, let's say your tree has built up something like C, D, E, F, G, right? And now let's say you are trying to find the root of C. If you're trying to find the root of C, that means you'll go from C to D, then from D to E, then from E to F, then from F to G, and then you will return uh, G as the root. While doing that, if it was, we already done one traversal, right? Maybe do another traversal and point everybody to G itself. So you go C, D, E, and F. That will make your tree size much smaller. You will compress the size, right? And you can also do it simplistically in a single line with not actual path compression, but like an optimal path compression, which is something like, so when you're going from C to D, why don't you point C to the parent of E, right? So let me come to the core. What I mean by that is slight optimization essentially. Uh, so while I'm finding this root, I'll do C equals to parent of C, but before this, I could maybe also do like, or maybe after. So parent of C equals to parent of C. Does it make any sense? If I just add this bit, just this one line, it will also help slightly in reducing the. Uh, so I had this A, B, C, D, E, F. Let's say this was built up, right? And what I would do is I would, when I'm trying to find a path, I'll change for F's parent from E, I'll change it to D, right? So I'll have Initially it was here, then I'll change it to F now. Now I'll go to D. Now D's parent is C, but I'll change it to B. So what I will do then is essentially I'll remove this link and I'll add this link directly. Right? So we're essentially trying to compress the path in a better way, in a slight simple way. Just adding this one line, typically for a larger tree, will significantly improve your performance of your algorithm. So let's do this. Okay, we get a compile time error, and that we know why. That's just because we did not handle the indexing bit. But other than that, this should be good. All right. So that's all.